Preview. Preview.
Today we are going to see Carnot cycle. First of all, to understand the Carnot cycle, we must know about the basic concept of the thermodynamics, that is the thermodynamic properties. Thermodynamic states, processes and cycle. Before watching this video, you must have seen the thermodynamic basic video. Here we are going to take a small review. Thermodynamic properties. Properties are unique characteristics, and these properties are the point functions. We have already seen these in our first video. So pressure, temperature, volume and entropy, these are some of the properties of the thermodynamic system. These are most important properties. When piston moves from one end to another end, means from TDC to BDC or from IDC to ODC. Here this is a vertical piston and cylinder arrangement. Both pistons and cylinder are shown on the figure. What will happen when piston changes its position? Here at a BDC, pressure, temperature and volume and entropy are P1, T1, V1 and S1. So at TDC, P2, V2, T2 and S2. These are the properties. This change can be represented by using graph. So we know that on a graph, for example XY graph, there are two variables. So number of graph are equal to number of the combinations, and on one graph we require two variables to show any point. PV, TS, PT, PS, VT, VS, these are the combinations of the properties. By using this we can draw this type of graph, but PV and TS, two graphs are most important. So these are the two graphs, PV and TS. By using this graph we can show any process, any cycle or any state. So this is piston and cylinder arrangement. There are two ends, that is BDC and TDC. So at BDC, P1, V1 are the pressure and volume, and T1, S1 are the temperatures and entropy. These are the properties at BDC. Similarly at TDC, P2, V2 and T2, S2 are the properties are shown on the both PV and TS diagram. So point 1 is corresponding to BDC and point 2 is corresponding to the TDC. 1, 2, these are the state of the systems, and there are large number of paths we can draw between 1 and 2, means there are infinite paths, and this path is called as processes. Now thermodynamic process. In piston, when piston moves from TDC to BDC or BDC to TDC, there is a change in state of the system. So when system changes from one state to another, it passes through the number of equilibrium points, that is the points lies between 1 and 2. So these are the equilibrium points. So this is called as process. Path followed by system is called as process. So there are large number of paths, means there are large number of process may available, or system can follow any path, means system can follow any process. So total number of processes are infinite, means to reach from 1 to 2, system can follow any number of paths. So paths are shown on the figure. There are infinite path, means infinite processes. Now different types of processes, that is thermodynamic processes. Keep any one of the property as a constant, that is, we have seen that there are 4 properties, that these are the main properties. To obtaining extreme conditions, we keep any one property as a constant. So this is PV and TS diagram. So first process is constant pressure process, means also known as isobaric process. Here, when system changes from 1 to 2, there is constant pressure, so there is change in volume, but as well as change in temperature and entropy. Now second process, that is constant volume process. So when system changes from one state to another, there is change in pressure but volume remains constant. Also there is change in temperature and entropy. Now third one, that is constant temperature process. Here when system changes from one state to another, temperature remains constant but there is change in entropy, as well as pressure and volume of the system changes. Now fourth one, that is constant entropy. Here we have seen 4 properties, so we can keep any one of the property to get any process. So here entropy is constant when system changes from 1 to 2, but there is rise in temperature and change in pressure and volume. So P constant means pressure constant, so this process is known as isobaric. When volume is constant, this process is known as isobaric. When temperature is constant, this process is known as isothermal process, and when entropy constant is called as isoentropy or isentropic processes. Here we are going to see another process, that is when there is no addition or rejection of heat, means no change in heat. This process is called as adiabatic process. Now thermodynamic cycle. This is PV diagram, and there are 2 state are shown on the PV diagram. When system changes from one state to another, it passes through the number of equilibrium points, and this path followed by the system is called as process. So here process 1. Cycle consists of the number of the processes. So here condition is that final state of the last process is similar to the initial state of the first process. In this process, here process 1 and process 2 are shown, and this is the cycle. So in process 1, initial state 1, final state is 2, and process 2, in process 2, initial state is 2 and final state is 1. So here we can see that the final state of the last process is equal to the initial state of the first process. So here we can say that cycle is completed. So enclosed region is nothing but the cycle, that is closed loop. So cycle, there are minimum 2 processes are required to complete one cycle, and maximum may be infinite processes. So this is PV and TS diagram. If we draw a rectangle, that is cycle, so here area on a PV diagram is nothing but the length into height, or P into V. Similarly, area under the TS diagram is nothing but the T into S, that is entropy into temperature. So area on a PV diagram, or area under the PV diagram, is equal to P into V. So unit of pressure is Newton per meter square and unit of volume is meter cube. So finally we got unit of the area is nothing but the Newton meter, that is equal to the unit of the work done. So area under the PV diagram is nothing but the work done obtained from the cycle. Similarly we can see on a TS diagram. So here area on a TS diagram is nothing but the T into S. So here we know that the temperature, unit of the temperature is Kelvin, and unit of the entropy is kilojoule per Kelvin. So finally we got kilojoule as a unit of the area. Here area under the TS diagram will gives us the net heat utilized or used. So this is nothing but the Q addition minus Q rejection. When 100% conversion of the heat into work is done, means available heat area under the TS diagram, and work is nothing but the area under the PV diagram. So when available heat is equal to work obtained, then we can equate area under the TS and PV diagram. So this will be helpful to understand the Carnot cycle. Now we are going to see Carnot cycle. Carnot cycle is the ideal cycle, means we cannot achieve this in a practice. So this cycle is designed on a paper only. So cycle designed in such a way that cycle gives maximum work done or maximum utilization of the heat, that is nothing but the area under the PV and TS diagram. We can try on both diagram. So this is PV diagram. First of all, we are going to see only PV diagram. So this is a rectangle, and a rectangle is nothing but here cycle. Any area or any closed loop is a cycle. We can draw any type of area, means we can design any shape of area, means any shape of the cycle. Here we have observed that the rectangle gives the highest area, means if processes are arranged such a way that this gives a rectangle cycle, so here work done obtained on a PV diagram will be maximum. But this is impossible. Then we are going to see why this is impossible. Similarly, on a TS diagram we can draw different cycles, means we can obtain different areas. So similarly, a rectangle gives the maximum area, and here on a TS diagram, area under the TS diagram is nothing but the utilization of the heat. So maximum area means maximum utilization of the heat. So rectangle on a PV diagram means maximum work done obtained, and rectangle on a TS diagram means maximum heat utilized or maximum available heat. But we can obtain higher work done if utilization of the heat is higher. So higher work done is possible only if there is higher utilization of the or greater utilization of the heat. Hence second case gives highest heat utilization or highest useful of heat, so we can obtain highest work. So this is nothing but the Carnot cycle. So we know that the on a TS diagram rectangle means the Carnot cycle. So this is the PV and TS diagram for the Carnot cycle. 1 2 3 4, these are the 4 points. 1 2 is the process. So on a TS diagram we can show the processes. 1 2 is isentropic compression, 2 3 is constant temperature heat addition, 3 4 is nothing but the isentropic expansion, and 4 1 is constant temperature heat rejection. So here heat addition minus heat rejection is nothing but the amount of heat available. Similarly, we can draw on a PV diagram. That's 1 2 is isentropic compression, 2 3 is heat addition, 3 4 is expansion, and 4 1 is the heat rejection. So there are two different shape of the areas on a TS and PV diagram, but the area under these both the curve or cycle are the same. Now we are going to see why we call it as idle cycle, or why Carnot cycle is impossible to construct. So this is piston cylinder arrangement, TDC and BDC. These are the ends shown on a diagram. When piston changes its position from BDC to TDC, there will be change in properties of the system. So these properties we can show on a diagram. On a TS diagram, this is the isentropic compression. When piston moves from BDC to TDC, there is a rise in temperature at a constant entropy. So isentropic is nothing but, or isentropic means reversible adiabatic process, means there is no heat addition and rejection, and this is possible only when heat transfer or amount of heat rejected or addition is 0. So reversible adiabatic process is possible only if heat transfer is 0 or there is no heat transfer. So Q, small q, is rate of heat transfer. This is possible only when there is not enough time for the heat transfer, means piston must move with the very high speed, so there will be no time for the heat transfer. Similarly, constant temperature heat addition means when piston reaches to TDC, there is addition of heat. So constant temperature heat addition is possible only when the amount of heat added to the system, that is all heat, must get utilized for doing work done. So we know that the first law of the thermodynamics, that amount of heat added is used for the work done as well as for change in internal energy. So here, to keep temperature constant, there must be 0 rise in internal energy, or there should be no change in internal energy. And this is only possible only when piston speed is very slow or very low. When piston moves very slow from TDC to BDC, there is a time for achieving thermal equilibrium, means temperature becomes equal to the surrounding. And this variation or alternate change in speed of the piston, that is high speed for the isentropic and very slow speed for the isothermal process, we cannot obtain such a variable speed, that is change in speed for every process. So in a cycle, in a Carnot cycle, speed of the piston changes for 4 times. You can get more information in our classroom. Thank you for watching this video.